Okay, so in this video, we're going to take a look at oxidative phosphorylation, and we're drawing in the details of what happens during oxidative phosphorylation. So for this video, we need to draw a giant piece of a mitochondrion and all of the parts that go with it, right? And we need to think about what's happening within the mitochondrion. So let's draw a mitochondrion or a piece of it. And it's going to look a little odd. It's going to look a little bit like a rainbow. Okay, this is going to be the matrix of the mitochondrion. And then there is an inner membrane. Okay, I hope that's big enough. I'm going to just remind myself that this is the inner membrane by writing it in there. And then there's a space between the membranes and then an outer membrane, right? So I'm going to draw in my outer membrane. I'm going to make this outer membrane pretty skinny because I just really don't need to put a lot of information in it. So this is the outer membrane. And then we can call this the space between the membranes. Some people call it the intermembrane space, or the space between the membranes, okay? Now, when we're thinking about aerobic cellular respiration, we have to think about all of the pieces of it, and we'll start with glycolysis. Remember, ooh, that marker is really not a good one. Glycolysis happens out here in the cytosol, right, outside of the mitochondrion. And in glycolysis, we take one molecule of glucose, and we've made 2 pyruvates. We've made 2 ATP, yay, right? And 2 NADH. Now, what happens next? Well, these pyruvates travel through both membranes of the mitochondrion. They're transported into the matrix of the mitochondrion, where they go through the process of pyruvate oxidation and citric acid cycle, or the Krebs cycle, right? So I'm going to draw in, that's all happening in the matrix of the mitochondrion. So I'm going to draw in kind of the citric acid cycle and pyruvate oxidation, citric acid cycle and pyruvate oxidation. I guess I'll write that down. I keep spelling pyruvate wrong. Okay. And what kinds of products come out of pyruvate oxidation in the citric acid cycle? Well, let's see. We lose some carbon dioxide. So carbon dioxide is released. We make some ATP by substrate level phosphorylation. What else do we make? We make a lot of FADH2 and NADH. Right? Okay, what's next? Well, in oxidative phosphorylation, the energy that's in NADH and FADH2 is the high energy electrons are going to be used to drive oxidative phosphorylation. So we need to draw in parts of oxidative phosphorylation that we need. All of the molecules that are necessary include the electron transport chain. So let's put that electron transport chain in. Remember, the electron transport chain is a series of molecules that are contained in 4 big protein complexes. We're going to draw those in. I'm going to draw in my protein complexes here in green, I guess. Okay, and oh yeah, cytochrome C is out there, and here's my last one. Okay, so we've got protein complex 1, 2, 3, and 4. That's what we'll call them. This is all a part of the electron transport chain, right? And within the within these big protein complexes are members of the transport chain that can accept and donate electrons, right? That can be reduced and oxidized, that can engage or undergo redox reactions. And so I'm going to write those in a minute. You don't have to know all these. We're just going to stick them in. I'm going to stick in their letter designation so we know that they're there. but there's a flavin mononucleotide. There's FeS, an iron sulfur. There's something called ubiquinone, which is a lipid in the middle of the membrane there. There's cytochrome C. Oopsie, I should say cytochrome B. Another iron sulfur group. Cytochrome C1. Cytochrome C, which sits kind of on the surface and it can move around. Cytochrome A in the complex 4, and cytochrome A1. Okay. And also there's a couple others here too, FAD and another iron sulfur. Okay. Now, remember, from our understanding of the electron transport chain, the electron transport chain is going to take electrons from NADH or FADH2, accept electrons from NADH or FADH2, and those electrons are going to fall through the electron transport chain via redox reactions. They're going to fall from a place of high energy in NADH to a more and more stable location, all right? As they fall through the electron transport chain, they become more stable, they move to a more stable location. This is going to be energy releasing, isn't it? Okay, so let's draw that in. I guess we'll use pink if it works. What we're going to draw in are the flow of electrons, and I'm going to show 2 electrons flowing from NADH. And when NADH loses those electrons, what does it become? It loses electrons. It becomes oxidized again to NAD+. These electrons then move via redox reactions from molecule to molecule in the electron transport chain. So these electrons are represented here by the pink arrow, and they're flowing from iron sulfur to ubiquinone to cytochrome B to iron sulfur to cytochrome C1. These electrons are flowing to cytochrome C, cytochrome A, cytochrome A1. And where do the electrons finally end up? Where do they fall to? What is the final acceptor of these electrons? Oxygen. Remember, oxygen is the final acceptor of the electrons at the end of the electron transport chain. Oxygen is reduced. It picks up those electrons. It reacts with what? It reacts with it reacts with protons to form water, right? So it reacts with protons